Okay, we're live.
Okay, great. Thanks. So welcome everyone. I'm gonna give just another minute before jumping into the topic for people to just kind of join in. So let me give it a second and then I'll just start by introducing myself. Hope everyone's having a good Saturday. Appreciate also, it's been a great hour and we'll hopefully continue with that. Of course, I'm broadcasting here from a prop I needed to be able to, the hashtag Spartan series, we'll play them back. So jump in with those. This a couple of times, but I definitely, I'm going through a lot of material and it's very visual, but if there's anything that doesn't make sense, please ask to interrupt. And I'd much rather put things up early on, especially. Okay, I'll probably go ahead and just get started. Maybe just to start by introducing myself. So my name is Jim Ostrowski. I'm on the 971 Mountain View Spartan robotics team. It's actually my first year in the team, so I guess timing was interesting in that I haven't actually gone through a full round of competition. So I joined in last fall. I both went to Mountain View High School, but I could never rope them into doing robotics. But once they graduated, I decided it was time to join in. And I've been fortunate to work with a number of folks like Austin Shu and Brussels at my professional work, and they've roped me in and pulled me into Spartan robotics. So that's been fantastic. But I am really looking forward to getting to an actual event. And so hopefully we'll get to that over some of the course of next year. A little bit about me. So my background is in robotics. I've been working in robotics for university. I worked on a robot system, and then went to do graduate work, getting my master's and PhD at Caltech. Also working in robotics, mostly the mechanical side of robotics, mechanics and controls of robotic locomotion. So I worked on anything that moved, walking, flying, swimming, crawling, rolling. Literally, my thesis was about things that moved and how they locomote. From there, I went and taught for a while. So I spent right around 7 years at University of Pennsylvania. As a professor, I encourage you. It's a fantastic. I made the mistake of taking a sabbatical and joining a startup company out back in California, and just never went back. And so ended up at a place called Evolution Robotics, which is an Idea Lab company in Southern California, working on mostly vision-based control of robots. So using computer vision to identify objects in the world. So finding things like people or coverage, and then that evolved into figuring out where the robot is located in the world. So I worked on that localization problem quite a bit, and then that also evolved into working in the retail sector, doing long detecting objects that have been either intentionally or accidentally stolen from a store. There, in my most recent gig, I moved to the Bay Area. To work in robotics, kind of clear, the mostly known for their tractor manufacturing, but we are working with them to develop advanced technology with the goal, among many goals, but of helping farmers use less chemicals by applying just what's needed to individual plants. So that's been one of our main focuses, is how do you use technology to see and identify every single plant and apply just what's needed. Okay, so that wasn't too long-winded, but let me jump into camera calibration. It's something that we've been working on this season. So just as a quick, what is that? What do I mean by camera calibration? Spend a little bit of time talking about why that's important. And then I'll talk about how we've been doing intrinsic camera calibration. We'll say calibration. Camera calibration is basically being able to know the different aspects of a camera that tell you both where the camera is in the world, and that's the extrinsic calibration, and how the camera interprets the world, and that's more the intrinsic calibration. So if I think about intrinsic calibration, we focus typically about deviations from that pinhole model. And that has to do with like, where's the camera center actually located? What's the focal length? So if you've ever zoomed in and out on a camera, either a manual zoom or even with your phone, you're changing the focal length. You're changing the depth at which the focus happens. And then there are lens distortions. Lenses aren't perfect. Warping of the image. There's a few types of calibration. That was intrinsic. The extrinsic calibration is more about where that camera is relative to other things. So what's happening in the for the top on extrinsic calibration, it's really trying to figure out where the robot is, for example, for knowing information about our camera and where that camera is located with respect to the world. Intrinsic calibration is about figuring out where the camera is relative to other things. It could be the robot reference frame. It could be some target in the world. It could be something. So I have to include links in the talk that you could use to track through and the calibration. Excuse me, camera thinking about using OpenCV and links there. And I'll just also to maybe to ask if there are any questions at this point. Again, I'll dive into a lot more detail, but to highlight again, please, if you have any questions along the way, feel
Jim, we're getting some feedback that you're cutting in and out, so maybe potentially turning off your camera, that might help.
Yeah. And my internet's been a little bit flaky. Let's see. Sorry, I've got to find the Zoom app. It's not coming up immediately. All right, I'm going to drop out of presentation mode for just a second to see if I can track this down. Oh, there we go. Sorry, it was in the title bar. That made sense. Okay, so I'll turn off the video and see if that helps.
Great. And maybe if you just want to repeat what you were saying on this slide, just in case people missed that part. Thank you.
Okay, so internals of the camera. The lens where the camera, but that's where the camera is. Melissa, can you hear me still? Or
yes, I can hear you, but you're not presenting, so you might want to present again.
Okay. Yep. It looks like Zoom just dropped out and reconnected. So, okay.
Sounds a lot better now too. So
it sounds better too. Okay,
yeah.
Great. Let me just send one note real quick and. Okay. All right. So, and then I mentioned there's a reference to OpenCV, which is an open source computer vision set of libraries. It's really powerful. Highly recommend getting familiar with that if you're doing anything with computer vision. And please, if there are questions, and it seems like people have already been using this, if there are questions or comments, post them to Slido under the hashtag Spartan series, and we'll get them answered right away. And I'd love people just to throw out questions rather than, if anything's confusing, rather than people getting lost or being confused. I'd much rather have questions along the way. So thanks for that. Real quickly, just why is calibration important? Basically, when we're trying to figure out things about the world through the use of a camera, knowing accurately where things are is really critical. So if I'm off by 10 degrees on estimating where something is, I may send the robot heading off in the wrong direction, or my estimate of where the robot is in the world could be completely off. So getting that right is really critical. On the intrinsic side, very often we're dealing with cheap lenses, relatively cheap lenses, compared to kind of say a high-end camera lens. And they're very small. They may be plastic. Those can introduce a lot of distortion. So being able to correct for those distortions is really important. And their assembly may not be perfect. So there could be a lot of variation in the cameras. And so that's going to change where our estimates are on where things are in the world. So it again really impacts where we think things are, getting that intrinsic calibration right. And also if you're doing stereo camera, where you're using two cameras to estimate depth, you have to kind of triangulate off of that. And so if those cameras are off significantly in their intrinsics, then that estimate is going to be wrong. On the extrinsic side, again, where the camera is in the world, that's really important. If I want to think about an object in the world and where it is relative to the robot, and I don't know accurately where that camera is located in the robot system, robot reference frame, then I don't know that accurately, then all those errors are going to translate back to my estimates of where things are. So it's really important to have the cameras tied into a single reference frame relative to the robot. So that's part of the extrinsic calibration. Again, I'm not going to talk about that today, but more than just, I think, one slide, but that is also critical. And I do want to mention that, if you can't do this calibration, there are things you can do to kind of get close. And at the bare minimum, I think you have to take some type of measurements, whether it's just right out of CAD, and you're kind of assuming that things are assembled as they are relative to CAD and constructed as they are given in your CAD files, or take a tape measure and measure things out to understand where everything is relative to the robot. You can also do the same thing with intrinsics, and I'll talk about that, about how you could estimate what the ideal camera parameters are supposed to be. But with all of these, it's really hard to get good, accurate measurements, especially when you think about angles, getting those correct, especially when you've got compound angles and three degrees of freedom, really hard to measure. So having something that allows you to automatically do that is really important. And again, I'm just going to spend one slide on extrinsic calibration. I'm not going to spend much time on it, but just want to give you a flavor for what that is. Basically, the extrinsic calibration is a map that tells you, given some global reference frame, and that could be just the robot. It doesn't have to be truly global. It could be the robot reference frame, like where the IMU is located or the center of the wheels. Where is the camera relative to that? So if O is the origin of the reference frame, this say robot reference frame, and C is the origin of the camera reference frame, then it's the map between those two. So it tells you where the camera is located to the origin of the robot. So it might be, a meter above the origin of the robot and tilted down 10 degrees. That would be the type of extrinsic. And what's useful is it allows you to map points that you might see, so this image point that you see in the camera frame, and map it back to, say, a more global reference frame. Okay, so so that's extrinsic calibration. Again, I just want to mention it. There's lots of material on that, and that's going to be really important for us going forward, but I want to focus on the other half of calibration, which is intrinsic calibration. So to do intrinsic calibration, first thing we need to do is talk about what our model is for how a camera works. And that's called the perspective projection model. It's a pinhole model of a camera. And if you're familiar with this, it starts to make intuitive sense, but let me just walk through it, because if you've seen it for the first time, it can be an interesting new thing to look at. The idea is, if I've got my camera, and just kind of by tradition, we model a camera with the z-axis pointing out, so that's kind of pointing forward along the axis, the focal axis of the camera, x to the right and y down. So I'll use that type of coordinate reference frame mostly. So if I think about a point in the world relative to that reference frame, so it's got some point in the world, x, y, z coordinate, and I want to ask, where in the image does that point show up? Then I need to project it down to this center area is the image plane. This would be what the image looks like. And so I want to find what that point is for some point in the world relative to my camera, and where does it map to the image. So some of the notation I'll use is x, y, and z for the point in the world relative to the camera frame. So it's x, y, z coordinates, and how it maps to some UV coordinate in the image frame. And U is going to be how many pixels, kind of how many columns it is over in the image, and V will be how many rows down in the image it is. So, and another thing we do is we, again, by kind of tradition or the way it's evolved in the literature, the origin or 0, 0 in an image is the top left corner. So a point in the image I'll reference by these two coordinates, U and V. And then one of the things that's important in this diagram is the focal length. So what we do is with a pinhole model, we pretend that kind of all the points, we kind of project them all down to this camera origin where C is, but we project through this image plane. And there's a lot of details behind it that I'm a little bit covering up, but the image plane is measured some focal length away from the camera origin. And when we talk about things like a zoom lens, if you've ever used a camera and you hear about an 8mm lens or a 75mm lens or a 200mm lens for a long zoom, it's referring to how far is this image plane from the camera center. So I always think that's really interesting, is, talk about a zoom lens that maybe ranges from 75 to 200 millimeters. It's really referencing the image plane is 200 millimeters from this camera center in this pinhole model. And so moving that image plane out effectively zooms your image in. Okay, and we'll talk about that some more. But the first thing I want to get to is, how do I compute, sorry, let me go back real quick. How do I compute the point U and V that this thing projects to? So it's somehow got to be related to X, Y, and Z, and it tracks along that ray all the way to the camera center. So now I'm going to take just a vertical slice of this. So ignore the horizontal part, the U part, if you will, and just look at the V part, the vertical part. So I've just drawn that triangle with the camera center here on the right, my height above the camera measured in Y, like I did like from before. So this is that point that I was referencing, X, Y, Z. And then in the middle here would be the image plane, and it's projecting down to a point U and V. Again, I'm just looking at the vertical components of this, so the V component of it. So just to, I'm going to flip back to the other image so you can just kind of see what I'm talking about. So that triangle is the one that starts with C here on the right, goes up and comes down. And I'm just looking at the vertical portion of that. And then if you use geometry here, it becomes pretty clear. These are similar triangles. So this outer triangle is similar, shares a common angle to this inner triangle. And so just through similar triangles, I can give a relationship between these two. So I know that the relationship between Y and Z on the outer triangle should be equal to the ratio between V and F, where again, Y is the height of the point in the world, V is the height in the image plane, Z is the depth of that point, so how far it is from the camera center, and F is the focal length, how far the image plane is from the camera center. So I get this relationship. Or if I want to just compute what V is, I just bring F to the other side, and it's the focal length times the height above the camera times the divided by the depth. And similarly, I could do this for the horizontal one. It'll just be U is equal to F times X over Z. And so you can see what I'm effectively doing is just taking the height above the camera and dividing by the depth. So in each case, I'm dividing by the depth to get my image coordinate. Okay. I'll talk about this a little bit more, and then I'll take a pause just to ask for any other questions on this. But, there are two things that that we have to introduce that make this take it towards what we can really use in a camera, and just kind of two modifications to what I said to that kind of simplified version. One is that in general, like I said, we don't treat the center of the camera, the 0, origin, at the center of the image plane, kind of where camera, the Z-axis would go and pierce the image plane. That's not the origin. The origin, again, just by agreement, we take to be the upper left part of the corner. So I have to shift the center, the origin, by the where the camera intersects the image plane. So we call that point the principal point, and we call the coordinates of that CX and CY. So measured from the top left corner, the place where the Z-axis goes through the image plane is called CX and CY. And in an ideal camera, that'd be right in the middle of the image. But in practice, and this is an important part of intrinsic calibration, in practice, it's not actually in the center of the image. So we have to correct for it. And so one of the things we're going to do in calibration is measure what that CX and CY is. Similarly, focal length, if I look at this equation and just did a dimensional analysis, you'd realize that F really needs to be in pixels to make this all have this all make sense. So as much as we talk about the focal length being in a metric system like millimeters, for using the camera and being able to compute the coordinates in the image plane, we actually want it in pixels. And so what we'll do is measure the focal length in pixels. As it turns out, pixels aren't always square. So a pixel that's capturing light doesn't have to be square. So we can have a different focal length measured in pixels in the x-axis than in the y-axis. And so for that reason, we have two focal lengths, fx and fy. And the fx is the focal length measured in pixels along the x-axis, the horizontal, and fy is measured in the vertical axis. And they can be different. In most cases, for a lot of cameras we use today, that they are the same or very similar, but certain cameras have very non-square pixels, and so you have to deal with that. All right, and so maybe just to conclude this part of it, so that leads us to these equations where I've substituted fx and fy in for the focal length, and I've shifted by an offset based around the principal point. And that gives us the real projective equations we'll use to map any point in the world that's measured relative to the camera frame, how we get the point that it maps to when I actually look at it in the image. So if I see an object, say I see a ball that's out somewhere in the world, and I want to know, and I know where it is in the world, and I project that into the image, I can figure out where it should project into the camera frame using these projective equations. And as we go forward, I'm not going to talk about it today, but one of the things that's really important about this model is if I am given an image and I figure out where something is in the image, I can kind of back project and figure out where that ray is, where that object must have lied in the real world. So if I'm trying to figure out where something is in the world, these equations are what I need in order to at least figure out the ray in which the object lies. And then we can use other things to figure out the depth. And that's how we can start to figure out where something is in the world, in particular using something like size. If I know the size of the object, I can know its depth, and that gives me everything I need to know to pinpoint in the world where something is. Okay,
we have a question on the Slido. Do CX and CY represent the focal point?
They represent what's called the principal point. Yeah, sometimes some people call it the focal point, or the camera center is what I think of it as. So CX and CY represent, if 0, 0 is up here, CX and CY represent the point which the focal axis, which is the z-axis, intersects the image plane. And it can be hard to picture because with this diagram, because right here I've shown it going right through the middle of the image. But in practice, if the camera sensor is not mounted right in the center of the image, then it can be off the center point. So it doesn't actually have to be go right through the center of the image. Hopefully that made sense. Anything else? Let me again just pause for a second in case there are questions or before continuing on.
Nothing on the Slido at the moment, but I'll let you know.
Great. All right. Thanks. Okay, so those are the basic equations for a camera, and really, if you want to do anything with cameras, this is a great place to start. And again, I highly recommend put a link earlier into the documentation from OpenCV. There's some really good information there, as well as great functionality. So it's a good place to start also. And as much as I'd like to say that's it for intrinsic calibration, there's one other thing that comes along as part of the calibration, and it's a little more advanced, but I don't want to leave it out. So I'm not going to spend a ton of time on it, just give you a sense of it. But I'd make sure, I did want to make sure not to skip it completely. And that's camera lens distortion. And the reality is that as much as we have this pinhole model and we'd love for things to just map perfectly down the way that projective model works, the truth of the matter is that especially as we get wider and wider field of view lenses, that we get some distortion. And so there's different models for this. There's lots of different ways it can be modeled. The main type of distortions that we tend to see and deal with are radial distortions. And by that, it means that the distortion is basically proportional to how far you are from the camera center. So you get more and more distortion as you go out away towards the edges of the image. And especially with cheap lenses in real life, you get a lot of distortion. With things like fisheye lenses or very wide field of view lenses, it's almost impossible to avoid distortion. As you start to, and those typically are going to be this barrel type distortion or the positive radial distortion. That's the center figure there, where things kind of bend so that a line curves down towards the outside. If you're looking at a line going across the top of the image, it would bend down on the outside of the image. And so it looks kind of like a barrel is the barrel shape. If you look at the distortion that happens there. And that'll happen again with kind of fisheye type lenses. If you have a Ring doorbell, you've probably seen this, right? There's some distortion around the edges. And if you look at straight lines, they look curved just like this. The second type of distortion is kind of the opposite curvature type distortion called negative radial distortion, or more commonly called pincushion distortion. It looks a little bit like you put a pin in a sheet of paper, or a pin in something that bent it and deformed it, so that lines kind of, let's say towards the top, bend down in the middle, and you get this type of pincushion distortion. And this typically happens more with, say, long zoom lenses, and maybe is not as common with some of the lenses we use in 971. And just to give you a couple sample images, you can see here the barrel distortion. Again, along the center line, there's very little distortion. A straight line looks like a straight line, but this one's a pretty large distortion. But you can see what should be a straight line towards the top of the image gets very curved. Likewise, with the pincushion distortion, you see lines at the top of the image have now bent down towards the middle. The lines across the middle are basically straight, because it's, again, a radial distortion, meaning it gets worse as you go out along the radius.
Quickly, we have a question. How do you convert from pixels to millimeters?
Pixels to millimeters, yeah, great question. So I'll go back to this diagram. So when you think about millimeters here to pixels, millimeter, there are two things about the focal length and converting, and I'll talk a little bit more about how you use the camera field of view to do this. But if you had a focal length in millimeters, then what you need to know is what's the size of a pixel in millimeters, or usually they're given micrometers. So you take the pixel size and divide that. So a pixel, 1 pixel is how many millimeters, and then divide that into the focal length in millimeters as an example. And that's your conversion ratio to get from focal length in millimeters to a focal length in pixels. And I'll talk about another way to do it that if you don't want to go through this calibration process, but another way to do it that just uses the field of view of the camera and the image width in just a second. So I'll get into that. Okay, so there's this. And then I'm, again, not going to dive into these equations, but the idea of this distortion model is basically kind of scaled by the radius. So find the parameters, and here the parameters in this equation, I'll just look at the X equation, are the K1, K2, all the way through K6, as well as P1 and P2. Typically, in actually every application I've used, we've ignored the ones in the denominator here, the K4, K5, K6. And so we're just looking at kind of radial type distortions. So if R is the distance away from the center of the image, then we find these parameters that kind of tell us how much it warps based on how far it is from the center. And it's just taking the normalized distance, the X location divided by the Z depth, that coordinate, which is kind of getting towards you, and then just rescales it a little bit by these parameters. And then there's some other parameters here that are more around skew, that kind of couple X and Y together. Again, these get estimated as we work through the calibration. And this is something that is basically computed effectively for free by OpenCV. So it's nice to have the ability to unwarp things and undistort things, excuse me. Again, I don't want to spend too much time on this because you could go down a rabbit hole for a long time talking about just distortion. But I'll show you a couple of examples of it later when we get into this. But the idea being that we want to estimate these parameters, and then we can correct for them once we have this model. Okay, so let's get into the next section, which is like how do we actually get these intrinsic parameters estimated? So, and I'm going to talk about the way that we're doing it in 971 using OpenCV and some target patterns. But if you didn't have anything and you just want to use the ideal case, let's assume that I need those parameters, but I don't have a way of measuring them externally or estimating them. How do I just give an estimate that's kind of based on the ideal? Well, first of all, the lens distortion parameters would all be 0, right? So the ideal would be there's no distortion at all. And going back to here, I would just set all the K's and the P's to 0, and I'd just be left with X double prime equals X prime. because all I'm left with here is a 1. So basically everything drops out if I just set my lens distortion parameters to 0. So that's kind of the ideal case. And you could also kind of measure how much a line curves and come up with ways to doing that if you really wanted to. The principal point, also we've talked about already what the ideal looks like. It would just be the center of the image. So if W and H are the width and height of the camera image, how wide and how tall is it, then the center point of the image is just half of that, W over 2 and H over 2. And that would be the principal point of the camera. So we assume that the camera sensor, the sensor itself, the thing that's reading in the photons and the pixels, is perfectly in line with the lens. So the image center is right where the lens center is. And then lastly, focal length. And this goes back to a little bit to the question of how do I estimate focal length in pixels as opposed to millimeters. Another way of getting at it that kind of respects the difference between the horizontal and vertical field of view, pixel focal length, horizontal and vertical focal length, is to use the field of view. So if I know how wide my field of view is a camera, very often my lenses, like let's say, I think we're using a 70-degree field of view camera lens, horizontal field of view. Then I can use that to estimate that plus my image width to estimate what the focal length is. And here I've put a diagram together of where these equations come from. I'll just walk through it. So you can kind of see what this is about. So it's again, those similar triangles. In this case, what field of view tells me is what this angle is here, the angle of that triangle that we were using earlier in the relationships. And it turns out, well, what is that? That's half of the field of view, right? So that's, and here I'm just doing the vertical field of view. So if twice that angle would be the whole field of view, everything the camera can see. But so this is half of the vertical field of view. And then again, going back to just trig, right? The tangent of that angle would be the same as this height divided by the focal length. So, and this height is half of the image width. So it's H over 2. So if I want to put that all together, what I know is that tan of 1/2 FOV vertical is equal to H over 2 divided by FY. And then if I just rearrange those equations, I get Fy is equal to 1/2 H divided by the tangent of 1/2 field of view vertical. And that's a perfectly valid way if you just, you want to get a quick estimate of what those focal lengths are. In the ideal case, that'll give you the focal lengths. Okay, but how do we do it? So this is something that we've introduced this year into 971 is a way of estimating intrinsic parameters using target patterns. And traditionally, and especially for stereo cameras, these types of intrinsic and extrinsic calibration procedures using target patterns are well known and have been done for a number of years. Using lots of different types of targets. There have been just circle targets, little dots that are circles, checkerboard targets, so on and so forth. The goal here is to get lots of measurements of points in the camera. And the two things that I really need for this, one is get them accurately. So I really need to know where those points are accurately. So having like the center of a circle, a little dot that I can track, or with a checkerboard target, I'm looking at just the corners. So it gives me kind of narrowed down to just a pixel where that point might be in the image. And then a scale. So I need to know where things are relative to each other. So I need to know how big these squares are, as an example, in the checkerboard targets, or how far each of the dots are together relative to each other in circle targets. And once I do that, I can use that to estimate these camera parameters. So I can use that to figure out how much warping has gone on and estimate all the intrinsic camera parameters. For us, we're going to use what are called Charuco targets. So what's a Charuco target? Charuco target looks like this. It's just a picture of a Charuco target pattern. And Charuco stands for checkerboard plus Aruco. So Charuco comes from that. Nice portmanteau of those two words. Checkerboard, obviously just like a checkerboard, but I've added these little target patterns within it. So I've got all the boxes from a normal checkerboard pattern, but I've added in these Charuco targets, which are kind of like QR codes. They're basically little target pattern codes, and each one I can identify uniquely. And so the nice part about that, which is different, well, so let me take it back. With the checkerboard pattern, one of the nice things is I get really accurate corner points. So I have these very accurate points that are the corners of the pattern. I can localize down to a really sharp corner. But with the checkerboard pattern, I had to do a lot of work traditionally to figure out where each of these points were relative to each other, because I just get a bunch of points out in space and I need to figure out where they're all relative to each other. By putting these extra patterns in here, I can kind of identify exactly what point and where it is on the whole board overall. So I know a lot more about where everything is on this board by adding these extra target patterns. I also, because it's a printed board and I know more about it, I know the spacing of each of those two. So I have a scale factor. And I want to just mention scale because it may not have been obvious from what I've talked about so far, but scale is really important in understanding where things are in the world. And the way I think of it is, this example shows a good one, is these two checkerboard patterns. I can't tell the difference from a camera's perspective of a small checkerboard pattern that's close up versus a large checkerboard pattern that's very far away. And I liken it to, if I need to know where something is, if I have something that like lets me figure out where it is. If I close one eye, I can still estimate where something is based on maybe I've got one out every reason. Give me a sense of how far away it is. Difference between those two. Same thing in playing the robot game. If I've got a ball, for example, and I know how big that ball is, I could use the size of that ball to tell me how far away it is. And then lastly, for calibration, it's really useful to know that scale because it's going to help me identify where everything is relative on the in the camera frame. And also it's going to allow me to figure out where the target is relative to the camera. Okay, so using these Charuco target patterns as well as OpenCV functionality, we're now going to dive into how do we estimate the intrinsic calibration. And I'm not going to go full into the equations. I just want to walk through procedure for it because there's a lot of detail behind this. But I just want to kind of give you a sense, and I'll talk about the specific functionality that we call as I walk through it. And the procedure that I want to walk through is basically feature detection. So detecting the features plus doing the localization of where all the corners are in the checkerboard. We need to match up the 2D image points with the 3D checkerboard points. Estimation of the intrinsic calibration parameters, and I'll talk a little bit about getting pose from that. So understanding where the board is with respect to the camera. There are really good tutorials. I've provided some links on the Charuco aspect of this detection and calibration. So in terms of detecting the Charuco target pattern, Charuco patterns, there's a really nice piece of functionality. And so we're going to use a target board like this. And just want to give you maybe one more look at this. So on the left is the full board and what that looks like. If I zoom in a little bit, you see it's a bunch of the individual Charuco patterns, and then a single Charuco pattern here on the right looks like this. So it's got, it's a 5x5 grid. In our case, they have different, you can use different sizes, but a 5x5 grid of basically black or white cells, kind of like a 5 binary pattern that you can use to uniquely identify each marker. So when we do that, the nice part here is OpenCV provides a detect marker functionality. So I can go through and have it find all of the markers and all the corners for me. And it's pretty hard to see in this image, but right here is an ID for each of the markers. So every marker is uniquely identified, as well as the corner points that are around those markers. So wherever it's able to identify corner points and associating with markers, we get from this detect markers functionality, all the corner points that can be used. And again, what we're going to do is we're going to collect a bunch of these and use it to figure out what kind of warping and distortions are happening in the intrinsic calibration parameters of the camera. Okay, so in order to do intrinsic parameter estimation, doing it on one image is fine, but what we're going to do is collect a bunch of images that kind of cover the camera sensor. We want to make sure that we're capturing points all over the sensor, as well as from different angles, so that we get different projections of the plane down to the sensor. So I've just shown a few sample images and the features that get extracted from them. In practice, we use at least 30. I think currently we're using 50 images that get captured to generate a really nice, robust estimate. And we pass all of that data, all of the markers that have been detected, as well as knowing kind of what the target pattern looks like. So where these things are in 3D into this Calibrate Camera Charuco, and that's going to return for us the estimation of the camera parameters. And also with this, we can do an undistort. Actually, let me pause there and just make sure there aren't any questions, or ask if there are any questions.
There are no questions right now, but
Okay.
Perhaps some more will come in the next couple of minutes.
Sounds great. Okay, so I'll keep moving through this then. I, again, don't want to focus on distortion using the unwarping the barrel type parameters or the radial type distortions on the camera. But I just want to show an example of that. So this is kind of the original image that came out of the camera. And I don't know if you can exactly see it, but I'll show a zoomed in picture in a second, but there's some curvature here of the top edge of this pattern. So I promise you it's a straight line in real life. But the distortion, that's the type of distortion I was talking about, that barrel distortion. And by calibrating the camera, we're able to undistort the image. And so it looks something like this when it's undistorted. So that's the corrected image. I'll jump back to the original or undistorted image. Sorry, or distorted image. Sorry, the original image. So that has the barrel distortion in it, and this has the correction. And included a sample and see kind of a ton of distortion. You can see there's a bit of distortion, and then when I correct for it, it becomes basically a straight line again. So that's a really nice way to correct, and just gives an example of correcting the radial distortion of the camera. And again, I mentioned, you know, the OpenCV routines were returned the calibration parameters, the calibrate, but this basically has the horizontal focal length, vertical focal length. We've got square pixels. And then the center is estimated CX and CY, the principal point or center at 345 and 234. And what you can see is that these are actually fairly far from ideal in several cases. So the focal length, if I just use our ideal calculations, would have been 457. So compare that to the 390. And the camera center is also slightly off. The camera center for our ideal, which is just half the image, if it was right in the middle of the image, would be 320 pixels, because we have a 640 by 480 imager. So it would be 640 to get it right into the middle of the image. It would be 320. But we actually find that through the calibration process, it's 345 pixels. So it's a little bit off right of center. And the same thing with the vertical calibration. Instead of 240, it's 234. So it's a little bit above the center. And as I mentioned, the camera the distortion coefficients that I showed you, where we can do some corrections. So that's mostly it in terms of calibration. I do want to mention maybe a couple more things in terms of just kind of what you can do with this, but so I'll jump into this, and again, feel free to ask questions if there's anything on the intrinsics. This is more targeted towards extrinsics, but one of the things that's cool about this is we can estimate the relative position and orientation between the board and the camera. So how can we do this? Well, again, we're really relying on OpenCV, but the reason we can do it is because we know the scale of the board, we know where all those points are in 3D, and we've figured out where those points are in our image, and we can essentially use that to figure out where the camera must be relative to the board. So we've essentially computed, based on the scale and relative location of all the points, where the camera is relative to the board using our projective model. The camera center and board, and I find I'm able, the camera is relative to that board, and here I've just tried the draw axis functionality with an OP. Assume the corner. So another way of thinking this is I know now where the camera is relative to that board, relative to that axis on the board. So that's a really useful piece of information. Again, this is more on the extrinsic side. I'm figuring out where the camera is relative to the world, but I'm using to get that very accurate to correct for all of the distances in the camera. And this is the last thing I want to talk about is just kind of what do I do with that information? Again, I've talked a little bit about trying to figure out where things are on the field. So you can imagine that if I know a lot about my internal camera and I'm looking at a point in the world, I want to try and figure out where something is. I want to figure out where a goal is or where an object is that I want to pick up. And so I can use the ray that goes from the camera center through the image plane where that point is that I see in the image, project that out to the world. And if I know the depth of that point, I know where it is in the world. And so estimating objects on the field is really useful if I can figure out depth. And I might just use one way to get depth is to know the size of the object and measure the size in the image plane and basically infer depth from that. But so being able to infer depth of an object, also really valuable is if I've got multiple cameras on a robot, I was looking at the same board, and this is exactly what we do for stereo calibration. When I'm by stereo, what I mean is using two cameras that are looking kind of at a similar field of view and can estimate things like depth on it, just like we do with our eyes. We triangulate things in the world by using two views of it and figuring out where they intersect, and things that look closer are going to intersect more. Things that are further away, I should say, will look similar in the image. They kind of project down to a point that's more similar in the image versus things that are close up. The place where they project to on the image shifts a lot more, shifts further away. So I can basically use this board with a stereo pair, two cameras that are looking at the board, and figure out where those cameras are relative to each other because I know where each one is relative to the board. So I get an estimate for each camera of where it is relative to the board, just like in this picture. So I do that for both cameras. And now just using that geometry, I can figure out where the cameras are relative to each other. So that's really valuable especially for stereo, but also if I had two cameras mounted on a robot and I want to figure out where they are relative to each other, I can use the same idea. And then maybe more generally is using this target or some estimate of where things are in the world. And I might want to know where it is relative to an IMU or other parts on the system. So I can use something like this. And there's, I think this will be for a next time, there's this extrinsic pose estimation. One of the things we've been looking at is a routine called Calibr, K-A-L-I-B-R, that is a set of routines for using an IMU and a camera to figure out where they are relative to each other. So that could be really valuable for extrinsic calibration.
Jim, we have a question. Oh, hey,
yeah.
Questions.
Yep.
What makes the board so expensive?
Yes, that's a great question. Yeah, because they are, the large ones are, I think, a couple €100, I think, maybe a couple $100. The boards themselves are expensive. They are printed they're high quality print, first of all, so they're very accurate. They are a nice matte finish. They're also printed on a metal backing. So I don't know actually the technique they use to print, but I believe it's laminated on polyurethane. So polyurethane support structure, and then a metal backing on top of that. So it's a nice rigid structure, so it's not going to bend. You can kind of carry it around. So that's actually really important, is that it remain flat and rigid. But I mean, one thing to really understand is a lot of this can be done just printing out on a sheet of paper and mounting it as rigid as possible. So especially if you just want to play around with it, you can print this on a piece of paper and put it in front of your camera. And you just need to know the size of the squares. That's kind of one of the inputs to this. But everything else is relative to that. And so as much as those boards are very expensive, if you want to buy them commercially, you can make your own for fairly cheap. And your accuracy of calibration just comes to how well you can rigidly make that a flat board. That's a great question. Yeah.
We have a question here that says, what about homography?
Okay, homography. So homography is a deeper issue that doesn't necessarily, I mean, it doesn't necessarily have to do the calibration. It's good to have the calibration there. So homography is basically a mapping between two planes. So especially in the context of computer vision. So one plane we've got and know of is the image plane, right? So if I take an image, think of that as one plane, one planar slice. It's a that image plane. Maybe I'll go back to just that picture of it real quick. This picture. So I've got one image plane that is this would be my image. And very often what I want to do is take that image and map it somewhere else. So I want to rewarp it, remap it to something else. You can imagine one of the examples I really like is with bird's eye view camera systems. I don't know if you've ever seen these, but you can take cameras that say mounted on a car or a truck, and if you've got multiple cameras that are stationed around the car, you can stitch them all together to give what's effectively a bird's eye view, like a top-down view. Even though none of those cameras necessarily has that exact view, I can remap them to make it look like they were taken from above. And what I'm essentially doing is mapping this image plane to a ground plane, right? So I'm mapping one plane to another. That homography is basically, that map that tells me how do I take all the pixels in my image and map them to some other plane in the world. And the nice part is you can do this also with targets. As an example, we compute homography in 971 of image features on the, wow, I've already forgotten the name of it, but the station for where we're trying to shoot balls into with the current challenge. So if I think about that as a plane, we can figure out what that plane is relative to our image plane and understand how features would map between those two. So that's basically the homography. Where intrinsic calibration comes into play is if I want to get that correct and accurate, I need to know how to unwarp all the effects of the camera to get the undistorted image and then map that using my homography, right? If I try and just use the distorted version of it, then it's not truly an accurate map of the plane to the other plane. That was probably a long-winded way of answering that question. I'm not sure if I answered it. But
Awesome. We have a question that says, can you discuss the camera and lens system used by Team 971 and why was the system used over other products?
And sorry, camera and lens system, is that what you said?
Yeah, the camera and lens system used by Team 971.
Yeah, sure. So 971's using, we're actually using, I think we ended up with 4 cameras, but we started with 5 cameras. Basically one camera looking in each direction of the robot for localization, and one camera I guess you should be careful with how much I talk about that. I don't know how much of that's important to talk about or not, but and one camera looking kind of at the target. Um, the camera and lens, what we're looking for with a camera and lens combination is something that has very low distortion. So we wanted to have as little distortion as possible. So we're trying to get a good lens from that perspective. We want something with high camera sensitivity. So we want it to be able to work in relatively low light situations, especially indoor, you don't get much light. So we need something that is pretty sensitive, so it has a lot of light sensitivity. And what that drives is how long you have to keep your shutter open to get enough light in. And what keeping the shutter open in drives is how much blur you get when you're moving. So all of these factors kind of chain together. So you're trying to get, and that plays also in with the lens. So the lens aperture, basically how wide open the lens is, how much light it brings in, also plays into to how long you have to keep your shutter open, and therefore how much blur you get when the system moves. So those are all the kind of the factors that went into it. So it's kind of balancing aperture, how much light in terms of the lens selection, balancing how much light we get in, and how accurate, how much distortion you get out of the lens, as well as the depth of field. So where it focuses, how much depth. So this is basically comes down mostly to focal length and aperture. And so that was what drove the choice. And as kind of I showed earlier, we got a lens with relatively low distortion. We did have a really nice combination in terms of the light that comes in. I think we've done pretty good job there. I think that's most. Oh, and then obviously wanted as wide a field of view as we could get, so that we could see lots of points on the field. So we ended with, I think that's, and we've also experimented with 90-degree fields of view, and have even looked at wider field of view. The wider field of view, the more distortion you're going to get, and so there's kind of that trade-off about how much accuracy you want for each pixel. For that, you want narrow to see more of the field, and so that's why you go with a wider field of view. So kind of balancing those.
Great. And I think we have one last question.
Okay.
Is latency a driver for camera selection?
Yeah, so these are great questions. Yes, latency is always a factor. I should call it a factor in camera selection. Tends not to be a driver for camera selection for modern cameras. A rolling shutter, the latency there, you're talking on the order of milliseconds. Typically, that's much shorter than your processing time. So it's not going to drive time. And if you really need high accuracy, you can the latency cameras is fixed, so you get the same latency no matter what. So you report if you need to get the right timestamp on when the image was captured versus when it actually came into the imager. So I'd say it's a factor, but it typically isn't a driver because the latencies tend to be pretty good on most imagers. So we haven't seen that be an issue. Again, especially with what we're doing, the processing time on the image tends to be much greater than the latency.
Great, that's it.
Cool. Well, thanks everyone. Hopefully most of that made sense. And I'm sure we can figure out